A little bit of a background about me. I've been with Proto Labs for 10 years now. Prior to that, I worked in the automotive industry, where we would win a contract to take an envelope of space under a bonnet and design and develop a solution for the customer that would see us take the product through concept, testing, product development, all the way through to the final solution. We would then be the mass manufacturer of that product and supply it for the whole of the life of the vehicle, and then support end of life as well. In this presentation, I'm going to be discussing prototyping and the product development process, how that environment has evolved, and the considerations to have as you navigate from your revolutionary new idea to a finished mass-produced product. It's about a 20-minute prepared presentation. Feel free to ask questions throughout if you want, but there'll be a questions section at the end if you prefer. So who are we? Proto Labs is the world's fastest source for prototype and low-volume production parts. We help designers and engineers take their ideas from concepts to market much faster than they ever could before. We have a global presence. We've been in the EU since 2005. We were launched in the US in 1999. Within the EU, our manufacturing headquarters is in Shropshire, just north of here. But we also have manufacturing facilities in Finland and in Germany. And we have sales and technical support offices in Italy, France, Germany, Finland, and the UK. As well as that, we have a facility in Japan to support the market there. So, we offer 3 on-demand manufacturing services: 3D printing, CNC machining and turning, and injection molding. The unique thing about our services is we're able to produce parts from a 3D CAD model in as little as 1 business day. So our customers benefit from our services in a number of ways. Drastically reducing their product development lead times and the associated costs, helping them to develop world-class products that raise the bar for what can be achieved in their industries, as well as beating their competitors to market and gaining competitive advantage in their industry. So how does this translate in the real world? I thought I'd start with 2 definitions: product development and rapid prototyping. So product development, the process of design and creating and bringing new products to market to benefit customers. And rapid prototyping, techniques used to quickly fabricate a scale model using 3D CAD data. Construction of the part or assembly is usually done using 3D printing or additive layer manufacturing technology. And I think both of these definitions set the scene really well and still on the whole ring true. With product development, the standout phrase to me is to benefit a customer. This is something that's to remain at the forefront of our minds as we go through the product development process. And this is also something that can quite easily get lost when we are overwhelmed by the challenges we face through product development. With rapid prototyping, as we'll see today, the phrase usually done using 3D printing or additive is becoming less accurate. Rapid prototyping has evolved to something that is probably better defined as rapid manufacturing, and something we call digital manufacturing. So what are the common pitfalls with prototyping new products? Not enough planning, not knowing what the execution strategy is, not having milestones, what are the success measures? Experience, maybe this is the first time you've done this. Where can you get support, knowledge, or shared learnings? Cash flow. Prototyping costs money. This in itself is not a problem, but ensuring you spend it in the right way at the right time is the challenge. And of course, surprise setbacks, redesigns, spec changes can arise. Timing. Are timing plans realistic and achievable? Is the project being set up to potentially fail? Meeting customer expectations. Are you progressing to achieve what you originally won your customer over with, what your original concept was? Or do results from your test programs or changes in your customer needs result in last-minute design changes? And deadlines. How do last-minute changes affect the deadline? getting the balance right between virtual development and real hands-on development. If you had your product on your desk tomorrow, would you learn more about your current design proposal or not? There's no right or wrong answer to any of this, but having these considerations in mind is important. This all impacts your ability to control and successfully execute your product development program. So, why do we make things? Making things is human nature, be it from our origins in survival, sharpening bones to use as weapons or to use as equipment for food preparation, but nowadays much more to make life easier, to help people, to solve a problem, to make a living, or quite simply for pleasure or for fun. However, in the majority of scenarios for successful making, there are two common ingredients: a need and an idea that meets that need. Need can come from personal experience, be it observations made in society or market research that identifies an opportunity for success. Once you have the idea, what next? We'll all recognize this as a typical development process timeline from left to right. You start with lots of ingredients and snippets of ideas that contribute to achieving your bigger idea. As you refine the essence of the problem you're trying to solve and the profile of your customer, the specification and requirements of your product are defined more clearly, and your ingredients begin to get whittled down to ones that are going to contribute to your success. As we move further across to the right, you're moving firmly into the development phase of product design. Product design is well underway. Your product takes on a virtual life. You've created designs and are learning conceptually what is working and what is not. Something that is considered one of the most important steps of any product development is the next step, which is from virtual to real. Be it 3D printed parts, a fabricated proof of concept model, or a prototype injection molded parts. At this stage, the learning curve accelerates. Testing can take place, customer feedback can be received, and lessons learned start influencing design evolution. Critically, this is where iteration occurs. Design has many inputs, and this feedback loop is key to success. This window is the core of product development. This is where learning occurs. This is where many of the pitfalls of prototyping are experienced. This is the time frame all our planning and execution is trying to keep to a minimum. Iteration can be painful, but it's also key. If testing proves our designs do not work, then we must redesign, remanufacture, retest, and learn again. If our customer changes the specification, having seen our first concept prototype, then we must redesign, remanufacture, retest, and learn again. The output from this process is the finished product going to market. Whilst our goal is to keep this to a minimum, there are no rules as to what might be learned or required during product development. And the worst case scenario is you learn you followed the wrong concept path and you have to go back to idea generation and start again. Either way, this is costing you time, which materializes in the form of reduced cash, lost competitive advantage, delays to product launch, delays to revenue generation, and ultimately stress. Successful product development looks to minimize the negative impacts that can arise here. So traveling back in time to the 1950s, we see a typical engineering team. There's lots of people, very labor intensive, majority of time spent working alone in isolation. It doesn't look very collaborative. All designs are hand drawn on paper. There are no doubt some large filing cabinets somewhere where all these drawings are stored, never to be seen again. Iteration would have likely been very slow. By the 1970s, we're living in color. But apart from that, there are lots of similarities. Hand drawings, predominantly working in isolation, an environment of infrequent collaboration. By the 90s, computers were much more commonplace. AutoCAD 2D drawings. Drawings were probably still printed and hung in cabinets, but there was likely an electronic retrieval system that was promoting easier collaboration across the design team. And then through the 90s and into the millennium, 3D CAD became commonplace. Products being designed and assembled in full 3D, files stored in centralized database or transferred via FTP for faster access across a wider product development team. This was promoting collaboration amongst the teams. Iteration was much easier, and designs were captured in libraries of parts and individual part history trees for all to see. And also the introduction of FEA and assembly analysis tools that would help do a lot more design work and understanding of the design in a virtual environment prior to making the step and the costs involved of going to actual parts. And of course today, there are some amazing tools available, 100% online CAD software, live collaboration on a global scale. Iteration is possible faster than ever before. We've got mobile and cloud computing at the core of product design. If you edit a part on your mobile telephone, all your colleagues around the world can see it instantaneously. And FEA and simulation testing software as realistic as it has ever been, and results are generated almost instantaneously. So the standout themes we're seeing here, it's all about collaboration, reducing the time to get the final product design solution, and it's technology enabled. But a big, almost larger headline is how focused this all is on the virtual world. The virtual side of product development has made massive leaps and bounds to deliver this incredible environment. The creative landscape has completely changed to bring the best out of engineers and designers. But how has the real world prototyping and manufacturing evolved to keep up? How is the critical iteration phase of product development from virtual to real being supported? So prototyping and model making has evolved a lot over the years. From highly labor-intensive activities, handcrafted solutions to achieve a prototype, or sample product to fulfill a functional testing requirement. I'm sure we're all familiar with modeling foam. I never mastered the technique myself, but it's great for fine-tuning ergonomics. You can coat it and paint it to get surface finish and get a visual representation of a product. But again, it's pretty cool, but it's time-consuming and labor-intensive to work with. And fabrication and model-making techniques, whilst they should almost be considered an art in their own right, how are they meeting the needs of product developers today? And of course, there's 3D printing, a process that offers many benefits when it comes to getting part designs in hand as fast as possible. But this alone doesn't quite do it. What is needed is something much more aligned with the progress seen in virtual development tools. Processes that promote iteration, collaboration, and learning fast. A process that we call digital manufacturing. Digital manufacturing is technology enabled. It takes new and traditional manufacturing processes and revolutionizes them with software and hardware solutions that reduce costs and lead times, opening the floodgates to use manufacturing technologies that previously might have been seen as unsuitable or cost prohibitive for early stage, truly iterative product development, putting them into the hands of every designer as on-demand tools that drastically increase productivity. Digital manufacturing is built on a digital thread that starts with a 3D CAD model. Models are shared via the cloud for speed. Today, this enables our three manufacturing services: 3D printing, CNC machining and turning, and injection molding. With over 20 teraflops of computing power, we analyze your complete suite of components for each of your products and provide you back with manufacturing feedback that supports you design the best part for the manufacturing process that you're going to choose. As mentioned earlier, iteration is key to the process, and these manufacturing technologies complement this. It's very common to source first-round parts from 3D printing to check fit and function and feel, then progress to CNC machining to introduce the production intent material to start functional testing and learning from that, possibly in different materials to see how they perform differently, all very quickly through to molding some parts off tool, off process in the desired production intent material, and all of this in a matter of days. The design for manufacturer feedback that we offer is really cool. It supports increased right first time design. It's interactive tailored to every one of your components and the manufacturing process that you've chosen. And it's live pricing and engineering options, so you can tailor the output to see how it impacts your project. Faster iteration through concept to production intent part designs. Now let's move to materials. So here's where we are in the development process. I'm about to make our first step from virtual to real. Where do we start? Understanding what our objectives are at this stage of the development process influences our material considerations, which in turn influences our manufacturing process choices. Thinking of these technologies and processes as complementary to each other rather than competitive with each other is key to successfully capitalizing on them. Key considerations that went into choosing the material: intended application, what do you need the parts to do, what problem are you trying to what are you trying to prove or learn from the exercise, the complexity of the part design, and the volume of the manufacturing run. Importantly, with materials, sometimes the same material can be used across multiple manufacturing processes, which is your ideal scenario. But even more importantly, sometimes it can't. This table is a great example of the same material in different manufacturing processes. The different descriptions actually mean that in fact the materials aren't exactly the same. So there is another learning experience to go through as you iterate through manufacturing processes to your finished production parts. Now on to choosing a manufacturing service. We touched on it a little earlier. Understanding the objective of your iteration is critical to your decision-making process. Whilst the goal here is to go as fast as possible, unnecessary steps take extra time and increase costs, while not necessarily adding any value to your learning. Finding ways to minimize these steps will help your product development. The big question is not which process is best. They are all fabulous. It's how do we use each of these processes to achieve our desired objective. For me, this is a learning path from a digital solution to the large-scale manufacture of a successful product. So what's 3D printing, and what are the pros and cons? It's the process of layering material to build up a complex three-dimensional shape on a printer. So some positives with it: very fast turnaround of parts. Parts literally in a matter of days. It's great for low quantities. The more complex the part, the longer it takes to build and the more it costs. But it enables you to evaluate multiple design concepts simultaneously, helping you to learn faster. Negative with it: the material performance may not be representative of your intended production process, and it's not yet effective at volume manufacturing. And interestingly, a sort of positive and a negative with the process is you can make any geometry, which is really great. But if you're intending to take that geometry into a production environment off a different process, you've got to be very conscious that that design that you can make on a 3D printer can also be made in your chosen production process. So CNC machining. This is a subtractive process which starts with a billet of material which parts are machined out of. With it being a subtractive process, the more material removed, the greater the cost of the part, which could mean what you consider to be a simple geometry is surprisingly costly. But the positives with it, again, very fast turnaround. Production intent materials can be used, so you really start learning about your functional choices. And it's great for low volumes. However, there are also economies of scale that you can benefit from with the technology. Some negatives: typically it's likely to be more costly than 3D printing because of the introduction of the functional material, which costs more. And whilst it's a step closer to the production parts, they do not necessarily represent the properties of the production intent process. With CNC turning, very similar concept to machining, a subtractive process, but the raw material is bar stock rather than billet. And it's perfect for geometries that are naturally of a cylindrical shape. Positives with it: Live tooling, so non-cylindrical features can be added to the parts as part of the manufacturing process. It's cost effective for low quantities, production intent materials can be used still, and again, rapid turnaround. And a negative is it might be more expensive than your 3D printed parts. And finally, injection molding. So this is the process of cutting a cavity into a mold tool in the shape of your component and then shooting a resin or a liquid silicon rubber into that cavity to give you your part. Positives of this process is a very fast turnaround. Again, parts in as little as 1 business day. It's the production intent process and material. So it's a massive contribution to your learning. At this point, you are learning everything you need to know for mass manufacture. And you might be thinking that the prototype, you might be thinking it's only for prototype parts, but actually it's also perfect for rapid product launch, bridging a gap to your production tool being made so you can get your product out earlier than you thought you were able to. And it's great for low volumes, 25 parts, all the way through to much higher volumes, over 10,000 parts. Big economies of scale as you go up that volume range as well. Another real benefit from it is tools are guaranteed for the life of the project. So effectively, you can take unlimited shots. This feature really empowers the staying in control aspect for product developers. There's no future part supply commitment, and this full suite of digital capabilities are now truly on demand for people to use freely as and when they need in their product development cycle. A con with the injection molded process, or a downside, is there's of course the initial cost to have the tool manufactured, and also if there are any changes to the part design, that would likely require a mold modification or potentially a whole new tool. Which brings us nicely on to cost considerations. So digital manufacturing offers price points for every prototyping budget. As engineering performance demands evolve, the associated costing roadmap is clear from the outset. So you can better plan and better understand your cost control right from the beginning of your project and have no surprises in that environment as you progress through your development. The key factors influencing the cost, material choice, manufacturing process, and part complexity. And you can see there the kind of range of pricing as you move through the combination of those factors. But by taking time out of these processes, it's possible to greatly reduce the costs. Supported by digital resources means iterative steps are also made with more confidence, further reducing project man-hours. So on to engineering and business support. Critically, digital manufacturing and digital product development tools only enhance human collaboration. They are not intended to replace it. A number of the documents referenced today, and there are many more engineering resources such as design tips and guidance available on our website, completely complimentary, so please feel free to take a look. And really, this is trying to promote self-learning as and when needed. Should you wish to have a conversation with any of our engineering team, then we actually have a stand here today, stand 4650, which is just south of this auditorium, or just give us a call and we can put you in touch with people if you want to talk directly to our engineering team. So to conclude, virtual and real prototyping tools today are working hand in hand more closely than they have ever done before. Digital manufacturing is complementing collaboration and iteration. The product development toolkit is also the most powerful it has ever been. So really, with all these tools, it's in the hands of the engineers and designers around the world to capitalize on using those tools to revolutionize their product development cycle. Thank you very much. Any questions? Hello.
Right, can you hear me? You're giving those prices for that component. Does that include the original CAD design of the thing? I mean, say I bring you a design in the first place, don't I? And that's the price of you making it, presumably.
Yep, exactly that. You'd bring a design to us, and then the prices would be for us just to make it.
Okay, right. Can I ask another question?
Sure.
I think you said finite element analysis. Presumably, I just need to learn this somewhere else. What finite element analysis is?
Yeah.
That's presumably just varying things a bit.
Basically, it's a software technology that will take a CAD model. So you could construct a bicycle on a computer system and then apply loads to areas of it. So if you knew the weight of the rider, and the computer will simulate the impact on your design. So it's a virtual way. You might learn that your component fails. It might teach you to add a strengthening rib, or you go and add a rib, then you run it again and it works fine. So FEA is to have that environment in a virtual environment.
One other thing is, you haven't mentioned the patenting side of things, because obviously if you're wanting to make a prototype, you may be looking to patent it, and of course then the issue comes, well, if I come to you with a prototype, obviously there's a confidentiality and so forth. I don't know whether you could expand on that. Do you presumably do NDAs with?
Yep. So from our point of view, all our relationships occur in a confidential environment. So we have an NDA with every one of our, people we're talking to or customers. Personally, as an organisation, we're not involved in the legal or patenting side of things. So you kind of go to another provider for that. But in terms of our relationship, it would be in a confidential environment.
Okay then.
Thanks very much.
Hi, Sorry. Thank you very much. Very interesting talk. I have one question. So on the injection molding, have you found we've seen a lot of 3D printed molds for the injection molding. So have you done much of that, or how have you found it? Do you do it, or do you have a comment?
We haven't got into 3D printing molds themselves yet. But that's not, people order parts from us. That's not to say they couldn't print. If their part was a mold, they would print it and have it.
Oh, well, I was more thinking, say, to reduce the cost of the injection molding process, especially for short runs. So I was just wondering if you tried it, or because I've seen some stuff about it, but I don't know if it's how well it works.
From our point of view at this minute, we're still offering tools in aluminium. So we find there are a lot of benefits to the life of the tool, and actually because of many of our processes are automated, so heavily software driven. We've got the cost of a tool down in aluminium to a level that we're finding, the market likes it. It's very affordable. So our tooling starts at £995, including 25 samples. So at this minute in time, we're very familiar with the idea of 3D printing the tools themselves. It's getting the balance right of how that fits into our business.
Just wanted to ask. And then do you do any, we'll say, laser cutting, say, to try and get a quick prototype? Do you try and use laser cutting, or do you find it useful, or?
We don't, no, again, we don't at the minute. We offer all our prototypes in as little as a business day. So if laser cutting was going to revolutionise that down to an hour, we might be interested, but we're already in a business day, so we're pretty happy.
That's fine. Thank you very much.
Cheers.